Welcome to Astronomy Speakers Night at the David Dunlop Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlop Observatory. I'm delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. Please take a moment to say hi in the YouTube chat and tell us where you're joining us from. This helps us make sure that our technology is working properly, and that's important these days. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlop Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we do miss working from the DDO facility, we are so happy to bring you tonight's lecture through this webcast instead. We would like to start by acknowledging that the David Dunlop Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge that this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous peoples for sharing this land with us. It's my great pleasure to introduce our speaker for tonight's lecture, Dr. Katie Breivik. Dr. Breivik is a Flatiron Research Fellow at the Flatiron Institute Center for Computational Astrophysics, where she works to understand how gravitational wave observations can be used to study how black holes and neutron stars form. Outside of work, you will most likely find her watching Jeopardy or taking walks throughout Brooklyn. Tonight, Dr. Breivik's lecture is titled Whispers from the Cosmos and examines gravitational waves. If you, our viewers, have questions for Katie, please do ask them in the YouTube chat. She will have some time at the end of her talk to take questions. Please join me in welcoming Dr. Katie Breivik.
Thanks, Denise. I'm very excited to be here with everyone tonight. And I'm really excited to share some of the work that I and thousands of other astronomers have been doing for the past few years and decades to try to understand gravitational waves. Before I take off and start talking science, I always like to give a little bit of an introduction to myself and how I got into astronomy, because that's often one of the most exciting and fun questions to answer. And so I like to get to it right away. So I grew up in Utah in the United States, and on the border between Utah and Idaho is a lake, this lake called Bear Lake. My family and I, during the first maybe 18 years of my life, spent almost every weekend on the shores of this lake because we built a cabin by hand. So that was really helpful because it taught me a lot of things about how to build, and it got me outside, and it was really fantastic. But also it wasn't great for my social life. So that's a thing that I appreciate, but also was very grumpy about as a teenager. However, when I was not being grumpy and looking out across the lake, I would look instead back at the sky. And this is the sky at our cabin. This is an image showing the Milky Way, and the dust and the dark parts that you can see is actual dust in our galaxy. And you can see that there are literally tens of thousands of stars. So I spent almost every weekend looking up at this sky, and it was so filled with stars that it felt like the sky was looking back at me. So it's kind of almost not surprising at all that I would become an astronomer later on, because this was literally how I spent the majority of my growing up. Now, I'm not the first person to stare at these stars. Humans have stared at the stars for as long as we've known to look up at the sky, and we've always wondered what they are. Where do they come from? Why are they shining? We've actually studied the stars with telescopes all the way since Galileo turned a microscope up to the sky and could see things like planets moving across the sky, and he could see things like Saturn's rings. So we've been studying these stars for hundreds and hundreds of years. So you might assume that we totally understand how they work. We know how physics works mostly here on Earth. We know it well enough that I can be talking to you through Zoom and through YouTube and the internet. So obviously, if we can figure out how physics works here on Earth, maybe we can figure out how the stars work. Unfortunately, that's not totally the case. And there's one really, really important reason for that. And that is that stars evolve incredibly slowly. This is an image of an enormous star called Eta Carina that actually might be a pair of stars, but there's something like 300 times the mass of our sun inside of this object that you see sort of moving out. Now, what's happening here is actual real-time movement of this star, Eta Carina. And the reason that we know that this is happening is because the Hubble Space Telescope took pictures over the years of 1995 all the way up to 2008. And what Hubble showed us is that this gas is actually expanding. And the reason that you can tell that it's expanding is those two kind of bluish points up in the corner. Those bluish points serve as sort of a reference. They show us that this gas is moving relative to those two stars in the background that aren't. This means that we are watching this type of explosion happening in real time. This is one of the only stars in the universe that we really get to watch go through this on human timescales. If we want to compare it to human timescales, this is what I thought of during 1995 to 2008. So in 1995, I started kindergarten. I was a little tiny kid, still very excited about astronomy, only had looked at stars for a few years at that time. But as Eta Carina expanded only this tiny, tiny amount, I went all the way from kindergarten up and graduated high school. So while a ton of things happened to me over my lifetime, over my education, basically, this star was just barely thinking about maybe making a sneeze. In fact, stars really, like our sun, evolved for literally billions of years. So it's no surprise that we can't just watch a video of the stars evolving. So instead, astronomers have to get creative. And in the same way that we can study people, astronomers can study the stars. One of the ways that we do that is just by looking at populations of people. We take a census every few years, right? You have to figure out what kinds of people live in your country to try to help provide for those people. And so you take a snapshot and you say, this is how many old people there are. This is how many young people there are. And in that same way, we can do the same thing with the stars. We can take a picture and we sort of get a snapshot of a population of stars, but we don't get to see the whole picture. And just the same way that a census doesn't really tell you everything about the culture of a star, and you need to go back in history, we can do the same thing. We can actually study things like these Anasazi ruins that are in Utah, in southern Utah. We can study the things that are left behind from stars long gone by. And we can study those remnants to try to piece together how those stars lived their lives and how they might be different from the stars that we can currently take pictures of today. Now, as an astronomer, it's a lot easier to study stars that are shining bright because our telescopes pick up light. If you want to study dead stars, it's actually really quite difficult because dead stars, things like neutron stars and black holes, by definition, don't really emit light. Black holes, in fact, are the absence of light that we see. We see just a shadow if we try to take a picture of a black hole. So if you want to study black holes and neutron stars, we actually don't really use telescopes the way that the DDO telescope works. Instead, we use something else. We use gravity. Now, if you want to study gravity, the best person in the world to learn from is, of course, Einstein. Einstein is every gravitational wave physicist's favorite scientist, and you'll figure out why in just a little bit. So to get started thinking about gravity and how it works, we start a little bit back. And we start with Einstein's theory of special relativity, which he wrote down. It was a momentous occasion in 1905. And special relativity is actually the origin of that famous E equals mc squared law that we all know and love, right? That we hear all the time. What that theory actually means in one sentence is that nothing travels faster than the speed of light. So Einstein wrote down this theory. It's a beautiful theory. It literally explains why light is emitted. It explains how electric signals work, how magnetism works. It's fantastic. And so when he wrote this down, he was extremely excited. But like every physicist must do when they first present a theory, they have to put it to the test. And so special relativity did pass the test of explaining electricity and magnetism. And so the next place that he went was to gravity. We already had a theory of gravity in 1905, Isaac Newton's theory of gravity. And Isaac Newton's theory of gravity had stood a lot of tests for hundreds and hundreds of years. Specifically, Isaac Newton's gravity could tell us exactly how the planets orbit the sun. It could tell us exactly how the moon orbits the Earth. And so if Einstein's theory was going to stand up, special relativity had to also explain how gravity works as well. So to figure out whether special relativity works with gravity, Einstein did a thought experiment. He thought about the Earth rotating around the sun, like you see here. But he asked the question, what would happen if the sun disappeared? Of course, if the sun is gone, there's nothing for the Earth to be orbiting. So the Earth won't continue orbiting like you see there. It probably won't stop like you see here. Instead, it will take off on the direction that it was last headed before the sun had disappeared. And Isaac Newton's theory of gravity says that it would take off instantaneously. The moment that the sun was gone, the gravity would be gone as well. However, that made sense to Einstein. Of course, Newton's theory of gravity, he had studied it very carefully, but he thought about it a different way. And he asked the question, how long would we here on Earth know? How long would it take us to figure out that the sun had been taken away? And he thought and thought and thought and realized, oh no, this actually maybe doesn't work out so well because I know the speed of light. That's the theory of special relativity. It tells me that the speed of light is a finite number. And indeed, the amount of time that it would take light to travel from the sun to the Earth is 8 minutes. So now he has two different answers to this question of what would happen if the sun disappeared. It could either take off instantaneously because the gravity moved instantaneously, or it would take 8 minutes because that's how fast light traveled. Now remember, the whole point of special relativity is that nothing travels faster than the speed of light. And so in 1915, it took 10 years for Einstein to figure this out, that he had to come up with a way to make it so that even gravity couldn't travel faster than the speed of light. The picture that we had from Einstein was basically like one like this. Before Einstein, from Isaac Newton. It was this picture where gravity was just always this force that pulled objects such that they could orbit around a body. If you have mass, you have gravity. That, as I said before, doesn't work so well. And so Einstein had to figure out a way to transform this gravity that moved instantaneously into something that actually has a finite speed. And the way that he did this was to rethink not necessarily gravity, but the grid that you see below these two black holes, which I love. So I had to have those on there. So instead of thinking about mass or exactly what gravity is, he thought, okay, what's going on with this grid? And he realized that that's the problem with the way that we were thinking about this. We were thinking that this grid underneath the black holes is completely stationary. And so Einstein thought and thought, and he talked to a bunch of mathematicians. He learned a ton about geometry, and he came to the conclusion that really the way that we should be thinking about gravity is not as this instantaneous force, but instead as a manifestation of objects having mass. So in this formulation, which is called Einstein's theory of general relativity, what this means is that if you are an object that has mass, you curve the space that we live in. You can see that curvature by the small curved lines. A really fantastic result out of general relativity was that Einstein's theory could still explain everything that Newton's theory could, but also answered that thought question that he had come up with. And the reason for this is because he realized that gravity itself is just curvature in space. And as he wrote down the equations of general relativity, he also learned that space and time also move with the same speed, the speed of light. Now, in this formulation, if I take that black hole away, then the space is going to move exactly at the speed of light. And this object that's orbiting it will learn that it has moved once the space has become flat again. That means that if we now think about the question of how soon would the Earth know that the sun had gone, it turns out that the Earth's orbit would change exactly the 8 minutes that it takes the light to get from the sun to us. And so now we've solved that problem, and we have this fantastically beautiful, elegant theory of general relativity that not only can explain the problem of light and gravity traveling at the same speed, but it also explains Newton's theory of gravity. So it really has stood the test of time all the way since 1915. Now, if you think about what's happening here on the screen, we have this object orbiting, and if every object that has mass causes a curvature in the space below it and in it that it lives in, then something that's moving through that space and causing the curvature might actually cause ripples, right? Because the space doesn't just stay fixed. And indeed, there are these ripples that are caused in space. We call them gravitational waves. They're waves very similar to the types of waves that you would see in a lake, like Bear Lake, or in the ocean. And these waves are stretches and squashes of space caused by the most heavy and dense objects in our universe. So what do these waves actually do to space as they travel by? Well, if you imagine a gravitational wave propagating out from these two black holes, and you were able to put a grid of points just up in space. Luckily, I have this nice slide that can do it for me. We can actually write down from Einstein's theory exactly what these points will do. And as a wave travels directly into the screen or out of the screen to these points, it stretches and squashes them. It stretches and squashes them in extremely predictable and understandable ways. And that will become really important when we figure out exactly how big these waves are from gravitational waves. So I've told you that gravitational waves exist and they're stretching and squashing space. I've told you that everything that has mass curves space-time, and everything that's rippling in the that's orbiting in the universe causes gravitational waves. So why don't we feel them right now? Maybe we feel them? No, we don't feel them. And there's one reason why we really don't feel the gravitational waves stretching and squashing us, even though they are passing through us literally all the time. The reason for that came in 1916. Einstein wrote down, after his theory of general relativity, he wrote another paper that said gravitational waves exist, but they are absolutely way too small to detect or observe. And the reason for that is because the amount that they stretch space is a factor of 10 to the minus 21. So that's scientific notation, but we can write it out. That space stretch is a 0, a dot, and 21 zeros before you get to the 1. That is so mind-blowingly small. If we put it into context, a 0, a dot, and 6 zeros is the width of a hair. A 0, a dot, and 10 zeros is the size of an atom. A 0, a dot, and 14 zeros is the size of a nucleus. And we're still 1,000,000 times too big. So you and I are made of these atoms, and the amount that space stretches and squishes us all the time is 1,000,000 times smaller than those atoms. So it's no wonder that we don't feel this. It's no wonder that these stretches and squashes, we didn't learn about or didn't observe them until very, very, very recently. But it turns out that because they cause such very clear and predictable deviations in space around us, it does this stretch and squash, physicists were optimistic. Physicists believed that they could search for these types of objects if we could only figure out exactly how to measure these stretches and squashes. Now, Einstein predicted this in 1916. It's 2021. A lot of time passed between then and now. And right now, we live in the future. And the future contains something called the LIGO-Virgo collaboration. The LIGO-Virgo collaboration is a scientific collaboration made up of thousands of astronomers and physicists and engineers, both in the United States and in Italy. So on the left there, that's one of the detectors. That detector is in Louisiana. There's another detector in the middle in Washington State, which is sort of like a desert, very different from Louisiana, as you can see. And the one on the right is in Italy. So LIGO is the two detectors on the left, and Virgo is in Italy. And you'll notice that these types of detectors that are searching for gravitational waves, they don't look like a telescope. When you're able to go visit the DDO, it's not going to look like this. These are very, very special types of telescopes that really are just searching for stretches and squashes in space. Now, if I go back and I show you what this gravitational wave does, it'll make a lot more sense why our detectors are spaced this way and shaped this way. It's because gravitational waves take a detector and they stretch it and squash it, right? So that's not so surprising. The other thing that you might have noticed is that the bigger your detector is to begin with, the more it might stretch and squash from a gravitational wave. So these detectors are enormous. At the vertex of each of those two arms is buildings. So the arms themselves are kilometers on a side. Virgo is something like 2 kilometers, and LIGO, the detectors on the left, are 4 kilometers on a side. So these are enormous types of telescopes. And they work because of technology that Einstein didn't know about in the 1916 when he said that gravitational waves would never be existed. And that technology is lasers. So if we were to zoom in and be able to go directly into a LIGO detector when a gravitational wave passed by, we can actually simulate what it would look like. And it would look like this. LIGO works by shooting a laser down each one of these arms. And then the laser bounces back. And if a gravitational wave comes through, then we'll see that laser light pulse in a very predictable way. The reason that this works is called constructive and deconstructive interference. And because a laser can keep the exact same wavelength over the length of 4 kilometers, and we can set it up to perfectly destructively interfere unless a gravitational wave comes by, then that means that we can measure stretches and squashes in space that are even smaller than the width of the atoms that built our detector. When I say this, every time I talk about this, I get a little bit excited because I cannot believe that people have figured out how to do this. But it is totally the case that physics works, that science works, and that engineers are fantastic at their jobs to the point that this type of detector technology works. And you and I live at a time where we can put this technology to the test. Now, when I started my PhD at Northwestern in 2013, this was all just theoretical. We had built the detector, it existed, we had videos like this, we had done tests, but it took until 2015. And this is what the detector saw on September 14th, 2015. So I lied to you a little bit. The detector didn't see anything. The detector actually heard gravitational waves. That's why I call this talk Whispers from the Cosmos. It's because gravitational waves that our detectors are sensitive to are of frequencies that actually you can hear with your own ears. So the sound that you just heard was the sound of 2 black holes that crashed into each other 1 billion years ago, emitted an enormous tidal wave of gravitational waves that that very quickly, at the speed of light, in fact, traveled to us over 1 billion years As they traveled, they got smaller and smaller and smaller until they were smaller than the size of an atom, but they came through our detector. Now, we call this gravitational wave 150914. That's because of the year 2015, the month September, and the day 14. So September 14th, 2015. Now I want to break down what I'm showing you on the screen a little bit here to try to understand what's happening. So on the vertical axis of both detectors, I'm showing you both Hanford and Livingston. That is code. Those are the cities for Washington and Louisiana. This is the frequency of the wave that the detectors observed. And on the horizontal axis is the amount of time that the gravitational wave was in the detector. So you'll see that the amount of time is very, very short, less than a second. And the other thing that's really interesting to note is that the frequency of the wave increases with time. What this tells us is that the size of the orbit of the two black holes as they came together shrunk and shrunk and shrunk until they crashed into each other. And that's where the signal gets biggest and brightest, is right at that very, very high frequency. So this is exactly what gravitational waves look like. If you look at the line that I've shown, that's the actual amplitude of the wave. You can see that it gets bigger as the frequency increases and the black holes get closer together. And as I said before, and you heard before, we actually can hear this sound if we take the signal that the LIGO and Virgo detectors observe from this wave and just stick it into an iPod, basically. So that's one gravitational wave that we observed, the very first one, 150914. But LIGO's been running since, 2015. It's 2021. So there's more to this story. Now we know what 150914 was like, but then we got another detection. And once you have two detections, you can compare them. Hear the difference? It's easier to hear if we increase the pitch for you. So just by listening to what those two gravitational wave signals sound like from 151226, which was 2015, December 26th, and 150914, we can tell very important things. First, 151226 actually gets to a little bit higher of a pitch. Because it gets to a higher pitch, we actually know that that means that the black holes that crashed together were just a little bit smaller than the ones that crashed together with 150914. And the reason for that is because they can orbit a little bit faster, which gives us a higher frequency. So already, just from these two gravitational waves, we've learned that there are different sizes of black holes. Now, as I said, LIGO's been running. So we continued to run LIGO and Virgo, and we actually got some more interesting signals. So you'll see there's 150914 at the top. That was a really, really big one, very short. But each of these have different shapes. And again, you can see the different dates. All of the signals that you see, the first 5, those were all black holes. And those came in different years, 15 and 2017. So we actually turned off the detector for about a year to sort of make it better and make it more sensitive. They turned it back on in 2017. We saw a couple more black holes that crashed into each other. They were obviously different sizes from the other ones that we had observed. And then this signal came in. So what you're seeing right now is a signal from a gravitational wave called 170817. It came in on August 17th, 2017. And it looks way different from the black holes that we had observed. It also is running for a much longer amount of time. And if you listen very carefully, it's coming. It gets to a way higher frequency. This is very clearly a different signal, and it was a signal that we were very excited to observe. The reason that the signal could continue for over a minute actually, I guess just under a minute, sorry about that, is because it wasn't two black holes crashing into each other. In fact, it was a pair of neutron stars, which are much, much smaller than the giant black holes that crashed into each other to produce those previous gravitational waves. So by 2017, we had observed two kinds of gravitational wave signals, those from black holes crashing into each other and those from neutron stars crashing into each other. Now, in 2021, we've had 4 years since that last reported detection, and the LIGO-Virgo collaboration has not stopped. Just at the end of last year, they released the results of their third observing run. So this was the results of the first two observing runs, and now this is the result of their third observing run. So these are all of the gravitational wave events that we have observed so far. We call this our stellar graveyard because it's all of the black holes that we have observed with gravitational waves that are, of course, no longer living stars. Now, what I'm showing you here, for each, you'll see arrows for each sort of group of 3 blue or orange objects. You have 2 smaller ones that merge together to make a bigger one. Those are our black holes crashing into each other for the blue objects. And what you can see, if you wanted to get close and count, there are 38 pairs of merging black holes. 38. That's already more than we had found with telescopes using X-ray astronomy, which is something that I don't have time to talk about today. But in just 4 years, we discovered 38 pairs of merging black holes, and we observed them with these different masses. So on the lines that you see, those are the mass of those objects in units of the mass of our sun. And you can see that there are black holes with lots of different sizes. There are black holes that are 5 times the mass of our sun, and there are black holes that are 100 times the mass of our sun. It's an enormous range, and we're all super, super excited to try to understand these systems. And there's not only black holes, there are also 2 pairs of merging neutron stars, and even a combined, you can see an orange and a blue merging together to make a blue there. That's 1 black hole and 1 neutron star. So there are 41 gravitational waves that we've observed in 4 years. And from those things, we've learned a couple of really fantastic and exciting results, especially for folks like me who want to study these stellar graveyard objects. We've learned by counting up how long we've been observing, how sensitive our detectors are, and how many gravitational waves that we have observed, that pairs of black holes merge in our universe every 10 minutes. That means that since the time that I've been talking to you, 3 pairs of black holes have crashed into each other. That just makes me like so excited, and also kind of feel a little bit like wobbly, because my word, before 2015, we weren't sure that this happened. And what's even more exciting is even just from the few neutron star mergers that we have observed, we can count that up and know that pairs of neutron stars merge every single minute at some place in our universe. That means that there have been like 35 neutron stars that crashed into another neutron star, produced gravitational waves. Now, why haven't we observed these yet? It's because our detectors aren't sensitive enough. Our detectors can't see or hear every neutron star that crashes into another neutron star, or every black hole that crashes into another black hole. And that's just because they're not quite sensitive yet. But fear not, people are working to make our detectors more sensitive. And I am sure that gravitational wave astronomers and engineers won't rest until we're able to observe all of these black holes and all of these neutron stars. But in 2021, now that the detectors are off, there's one question on everyone's mind, and it's, where are these black holes and neutron stars coming from? And that's mostly what I try to think about all day, every day, as in my job as an astronomer at the Flatiron Institute. Now, there's one idea that they come, well, actually, let me take a step back. There's one very clear thing from us, which is that they likely come from stars, because we know that when very, very enormous stars, something like 100 times the mass of our sun, finish their life, they collapse into black holes. So we know that they come from stars, but we don't know the environments of the the stars that are producing these systems. This is one type of environment. It's called a globular cluster. It's called a globular cluster because astronomers are not particularly creative in naming something like this. It is a cluster of stars that looks like a glob. Now, while the naming isn't super exciting or just more than anything except descriptive, these systems are fantastically exciting to study. And that's because those stars that you see are so densely packed together that the black holes that are also lurking in these clusters, they can actually interact and form pairs, even if they didn't grow up together. And so what that means is that we can get pairs of black holes just by the black holes existing in these objects, which is super interesting and could potentially be the answer. Another answer that's maybe a little bit more simple is just that pairs of stars are born together, and those pairs of stars, when they die, collapse into black holes, and then those black holes eventually merge. That's also just as valid of an argument. This is actually the way that I study these types of systems. I simulate these pairs of stars to try to predict the kinds of black holes that might crash into each other and the kinds of gravitational wave signals that we would expect from them. So that's another option. They could just be coming from pairs of stars in our galaxy. Those pairs of stars don't live in these dense environments, so they probably don't crash into each other. They just sort of lead their nice, happy life together, make two black holes, and those black holes merge. And recently, there's been a really fantastic and exciting theory that has come out that the black holes could come from these really intense and high energy gaseous environments called AGN. An AGN stands for active galactic nucleus. And what that is gas that's swirling around. That's this orange gas that you see. And at the very back of that image, you can kind of see a really bright light that's around a dark spot. So what that's showing you is an artist's rendition of a supermassive black hole, a black hole that's something like 10 million times the mass of our sun. And it's sucking in all of this gas. So the gas is orbiting around in this disk. And inside of that disk, there could be stars. And if the stars exist in that disk, they could collapse to form black holes. And those black holes will orbit in this gas in a very particular way that might make them merge and produce the gravitational waves. Now, literally hundreds of astronomers, myself included, are all trying to work out explanations for each of these types of ways that you could make pairs of black holes merge. But the truth is we don't know the answer yet. And the reason for that is because it turns out that 38 pairs of black holes, 2 pairs of neutron stars, and 1 black hole and a neutron star crashing into each other isn't quite enough to rule in or rule out any of these figures. But that's okay, because as I told you, we're working to make our detectors better. We are working to upgrade them now. They'll turn on probably in a couple of years. It's a little bit hard to say right now. But the future is really, really, really bright for these objects. And the reason for that is because we're just on the precipice. You and I live at a time that's similar to the time in the few years after what the world went through when Galileo turned his telescope up to the stars. We've only had gravitational wave detectors operating for 6 years. I wonder what they thought was possible back hundreds and hundreds of years ago, just 6 years into using a telescope. Where will we be in 100 years? Hopefully we can answer this question and many more, like how pairs of stars live and die together. And so with that, I would like to leave you with the feeling and the thought that the future of gravitational wave astronomy is loud, because we will hear hundreds of thousands of mergers as we get better at detecting them and continue to observe. Thank you.
Thank you so much, Dr. Breivik. We are going to head now to Emma Seabrook for questions from our YouTube audience. Emma?
Thanks, Denise. Our first question comes in from Shaheen. He's asking, why are gravitational waves small and not massive, given the nature of the event that causes them?
That's a wonderful question. Thanks so much, Shaheen. The reason is that the systems that cause gravitational waves, pairs of black holes crashing into each other, are extremely far away. So space, which is getting ripples going through it, is really tense, actually. It's quite difficult to stretch and shrink space. That's probably good for us as humans, because I don't think that our bodies would like to be stretched and squashed as the space is stretched and squashed as we live in it. So if you were near where a black hole crashed into another black hole, your body would absolutely be ripped to shreds, actually, because the space is stretching and squashing on enormous scales. However, as the gravitational wave travels through space, the amplitude of the wave shrinks the longer that it has to get to us. And so the reason that they're so small is really just because they've had to travel such great distances to get to us, literally billions of light years. So they've traveled billions and billions of light years to get to us, and we can't be too upset at them for being small after that big travel.
Thank you. What a great answer. Our next question is from Marina. She's asking, did the waves of the two crashed black holes affect the Earth at all?
The waves, so they affected the Earth in that we could observe them. And again, luckily for us, they didn't really do much past that. It turns out that our detectors are so sensitive to be able to detect these tiny, tiny gravitational waves that they also detect a lot of other things. So in terms of what our detectors see, a tumbleweed rolling across the detector in Washington actually produces a bigger signal in our detector than the wave itself. So that's all to say, they did stretch and squash the Earth, but it was just by such a small amount that it probably didn't do anything to any of us here on Earth or any bit of the Earth, because the stretch and squash was smaller than the atoms that make up all that stuff.
Nice. Our next question comes in from Shaheen. Is LIGO listening to a specific region where we suspect a collision occurred, or is it listening omnidirectionally?
I love that question. So I'm going to take us back to pictures of the detectors just to make this point. So because it doesn't point like a telescope, Shaheen's intuition is really right on point. We can't, with a telescope, if you want to look in a direction, you need the mirror or the lens to catch the light coming from a specific direction. These types of detectors are more or less omnidirectional, which means that they can observe gravitational waves from almost anywhere on the sky. It turns out, because of the shape of the wave, they're better if the wave comes straight down. So from a direction straight down the top of the detector, because that's where you get the really optimal stretch and squash. But the other thing that's really interesting is because they're omnidirectional, they don't really tell us exactly where a gravitational wave came from. It's a little bit more like our ears. So with our eyes, I can tell you, my cat is sitting 2 feet away from me behind my computer because he's a weirdo. But if I was listening, I would only be able to tell, like, okay, there's probably a cat over there because I can kind of hear it. And that's kind of how these gravitational wave detectors work. They really work like echolocation type systems. And so that's why we have them spread all across the world, because if you observe a gravitational wave in one detector, then another one, you can actually use them like ears to sort of get a nice direction for where the wave is coming from.
Great answer. This next question is from Tim. If time slows in high gravity, how is it that black hole mergers seem to happen in about 1 second?
Oh boy, that's a brain bender of a question, and I love it. Okay, so you're gonna have to give me a second to think. I haven't thought about general relativity for a hot minute outside of this talk. So if the time slows down, the reason that time and space slow is because the gravity is so strong. But the objects, oh man, Tim, I don't think I have a good answer for you at this moment, because I'm as perplexed as you are. So let's come back to that question if we have other questions, and it'll sit in the back of my brain, and I bet you I can come up with a better answer.
Okay.
Because that's I want to be very real with everyone watching. This stuff is super hard even for the people who think about it all day, every day. So if your brain feels a little bit like mush, mine kind of does too. So if you ever feel that way, don't think that you shouldn't do science or think that you're not good enough to do science, because it's really hard for everyone.
Yeah. Maya wants to know if you could give a basic description of X-ray astronomy.
Oh, a basic description of X-ray astronomy. Sure. So we, as astronomers, we study all different kinds of light that come to us in the universe. And the same way that a gravitational wave has a wavelength, light also has a wavelength or a frequency. And X-rays are a certain very, very, very high frequency type of light wave. And it turns out that things that emit very, very high frequencies are things that are really, really hot. And so it's often things like hot gas that's being swirled around a black hole and moving extremely fast. And as the gas crashes into other gas that's traveling fast, it emits these really, really hot X-rays. And so that's actually how we have observed other signatures of what we think are black holes out in our galaxy, is because we see extremely hot gas, but we don't see a star or anything else. We just see a disk around something that's 10 times as big as our sun, but we don't see a sun. We just see the gas around it. And so we infer that a black hole lives there. And that's sort of how X-ray astronomy has helped us find those black holes.
Interesting. Linda asks, you said when they turn back on, referring to the detectors, you mean to say that they cannot be turned back on?
Oh, we've just turned them off because every few years we sort of incrementally make them more sensitive. So because these are the very first gravitational wave detectors to ever exist, we are extremely careful with them. We don't want to break them because, our governments have invested millions of dollars in them. And if you don't do things in increments, then there's a really high chance that you'll break the thing. And so the way that we do that then is, once they're sensitive enough to observe, we observe for a little while. And while we get a ton of gravitational wave observations as astronomers, the engineers are also studying the detector and saying, okay, we can make the mirrors that the laser bounces off of more shiny, or we can isolate the lasers way better, or things like that. And so what happens is they run for a few years, then we shut off for about a year, and they do upgrades, and then you run again for a few years, and then you shut off. And so we're in one of those shut off cycles, but they'll definitely be turning back on.
Cool. Blake wants to know, in your white paper entitled Stellar Multiplicity and Interdisciplinary Nexus, you suggest we need more information and greater understanding about binary star and multi-star systems, as it affects many branches of research in astronomy and cosmology. Is it fair to say that amateur astronomers measuring and reporting on double stars, doing citizen science perhaps from their backyard, can contribute in a small way to this endeavor?
Oh, yes. I am obsessed with the fact that somebody read that white paper. That's one of my most proud contributions to science, actually. So this is where I get to be on a soapbox a little bit. The point of that white paper was for me and my colleague, Adrian Price-Whalen, to convince all of astronomers that binary stars are the most important astronomy to do. And the reason that we hadn't figured it out yet is because we didn't have enough long-term data on lots and lots of binary stars. So the community of amateur astronomers that are submitting observations to databases like APAS, no, it's not APAS, the AAVSO, American Association of Variable Star Observers, that type of data is so important to our study of binary stars. So as a professional astronomer who gets paid to do this, I am so indebted to the amateurs who actually turn their telescopes up to the sky and observe, any type of star that they do, because that data is very precious to us and it doesn't come for free. So it's very important, and I really can't thank the amateurs enough for that. Because it really does impact our understanding of how stars evolve. Oh, I'm so chuffed. What a great question.
Thanks for telling us about your journey into astronomy.
Yeah,
one of the issues we at the DDO Online have been discussing, in recent months, is improving representation for minority groups, like people of color and women in astronomy. Can you tell us a bit about the challenges you might have faced getting into astronomy as a career? What would you suggest for young women who aspire to become astronomers?
Oh, so that's an interesting question. I think for me, one of the things that was really important that I didn't really have until I think maybe senior year of high school was somebody who told me that I could do science as a living. That wasn't, my family didn't really come from like an academic background. It was a lot of like, mostly accountants, I guess, which is quite weird that my whole family is accountants. But the thing that I ran into the most was when people said, what do you want to do? And I said, I want to be an astronomer. They said, that's not a job, which is like a little bit ridiculous looking back now, because like, hi, it's a job. I'm a real astronomer. But I think that that's one of the most important things is that if you are somebody who is mentoring somebody younger, or if you are a young person and you're interested in science, know that that interest isn't worthless. And know that just because you don't see scientists in your immediate life doesn't mean that we don't exist. Scientists do exist, and there are ways to find them. There are things like this type of program. This is why I like to talk to people through these types of programs. But also you can look on social media, you can watch programs on YouTube. Astronomers, biologists, physicists, we're all out there. And it is a career that you can do. So I think that was one of the biggest hurdles, just in general. And then on top of that, the only people that I knew who were doing any sort of technology things at all, of course, were dudes. That could be a function of just my background that I grew up with. It could be a function of the fact that, like I said, my family wasn't particularly academically minded. But yeah, for folks who are interested, if you are told that you can't do something, it's 2021. We know that that statement is trash. So don't listen to that. And if you have somebody who can help you and can mentor, you reach out to them and ask, like, never stop asking questions. That's my advice. And yeah, if you are somebody who doesn't have the answers, don't ever tell somebody that they can't do something just because you're not sure what the answer is. That's my other advice to adults.
Thank you. There's been a lot of interest in your white paper. Where can people find it?
I'm sure that we can put a link up or send out a link, but it's on something called the Archive, which is a totally sort of esoteric website. But there's a website that scientists all publish our work on for free called the Archive. I can definitely leave it with the organizers if folks want to read it. That's so delightful. Most astronomers try to not read we do. We like to read white papers, but everyone writes white papers. So it's kind of like the way that we communicate to each other outside of scientific literature.
Yeah, I think that's it for the questions from the audience. So thank you so much.
Thanks. Yeah, I'm going to really quickly go back to Tim's answer about why the gravitational waves continue to crash into each other. And Tim, I don't have a super great answer to this, except to say that what we observe is actually the event horizons crashing into each other. We don't see anything past those event horizons. And the black holes, as they crash into each other, they both are, nope, it's not happening. It's 8 p.m. I don't think that I have a good answer for this. I tried. Sorry, guys.
We actually got one last question that just came in. It's from Shaheen. Hopefully not a confusing question, but how do we differentiate distance versus magnitude? How do we know a small collision occurred close and not a large one very far away?
Really good intuition there. So this is distance to objects. in the universe at all is probably the most difficult thing that astronomers face, is knowing how far away something is. And that's because something could either be very far away and huge or very close and small. And one thing that's really, really cool about gravitational waves, I'm just going to show this picture here, I'm not going to play the whole video, is that we actually know how far away a gravitational wave is just by the total size that it is. So as it travels, it shrinks as it travels. Like literally, exactly. If it travels 2 times as far, it will be 2 times as small, the height of the wave. But the shape doesn't care how far away it is. The shape of the wave and how tightly packed those wiggles are, that's actually directly tied to the mass of the black holes. So every pair of black holes that crashes into each other has a different signature. And by knowing the signature that came in, we can literally reconstruct exactly the masses. So that's something that gravitational waves provide that really is, we're not going to get from light ever. So that's something that I am really, really interested in trying to understand how we can use that type of really precise information about the size of the black holes to understand about the stars that produce them. Yeah.
I think that's it then. That's all of our questions.
Those are some really, really fantastic questions. And thank you so much for asking them for me.
Thank you, Emma, for relaying all of those questions. And thank you so much, Katie, for taking the time to answer them. I will point out, Katie, if you do think of an answer for that question you missed, to send it to us, we can certainly pass that on to our viewers.
Definitely. I know that I can find an answer, Denise. It's out there. It's more that I am a star person, not a gravity person.
Perfect.